Spring 2018, week 5, problem number 2. All right, so problem number 2 is just talking about change of bases again, but in a more graphical way and in a more slightly detailed way. So let's get started. So problem A is essentially asking us the same thing. If we're given a vector 3, 5, and if we want to put that in the basis of 1, 1, 1, negative 1, which is to say that we want to describe it as a linear combination of the vectors 1, 1 and 1, negative 1, how do we do that? As we saw earlier, that's just going to be some alpha times 1, 1 plus some beta times 1, negative 1. And all we need to do is we have to find these alphas and betas. And to do that, we can write this as a system of linear equations where 3, 5 is equal to 1, 1, 1, negative 1 times a vector alpha beta. And so we know that the vector alpha beta has to be equal to this matrix 1, 1, 1, negative 1 inverse times 3, 5. So all we need to do is that we need to solve this system of equations to get to alpha and beta. And to solve the system of equations, we multiply it by the inverse. And so in general, given any vector v, so if this 3, 5 was any vector v, and we wanted to find what that vector v is in a basis beta, given by matrix B, and so if we wanted to find out what that vector is in that basis, we can say that this alpha beta, or also known as v beta, is equal to b inverse times v. And to write that more neatly, we can write that. Actually, I can just erase all of this. So basically what I'm trying to say is that v described by a basis b can be written as b inverse times v. And that's it. That's it for part A. For part B, we want to generalize this idea. And turns out this equation is exactly the equation that we'll end up getting. If you have a bunch of your basis vectors, so let's call them, so let's say your basis beta consists of vectors beta 1, beta 2, all the way up until beta n. Now we want to take any vector and we want to represent it in this basis. So all we need to do is that we need to take a matrix B that consists of these basis vectors, so beta 1 and beta n are going to be the columns of this matrix, just like we saw how the columns of B were the bases that we were dealing with. And then to put any vector in that basis, all we need to do is that we need to multiply the B inverse with that vector. And that's it. So for part C, we have to describe matrices instead of vectors in a basis. So far what we did was we had a vector v, and to describe it in a basis beta, all we had to do was to take b inverse times v, where b was a matrix that consisted of, like, its columns were vectors of beta. Now we want to do the same for matrices. And so basically what we want to be able to do is that we want to find out what an A beta would be. And turns out that this is just a little bit more complicated than for vectors. In general, we want one property to hold, and that property is that A beta times V beta should be equal to A times V in beta. So what am I trying to say here? Is that all I'm trying to say is that if I multiply any vector by that matrix, and if I take that into the basis beta, that should be equivalent to doing that whole computation in the basis beta in the first place. And so just like think about that for maybe 10 seconds. Like we want to be able to do some computation in the standard basis and then go to basis beta. And doing that computation in standard basis and going to basis beta should be equivalent to going to basis beta and then doing that computation. And actually, we can use this equation to find what A beta should be. what we're going to do is that we're going to take in the definition of V beta being equal to B inverse times V, and we're going to substitute it into this equation. So this equation gets substituted in here, and so we get that A beta times B inverse V should be equal to B inverse times AV, which is like writing this equation. And now what we can do is that we can multiply, on this equation, we can multiply B on both sides. And what we get is that, I just have to erase this part. What we end up getting is that B A beta B inverse times V is equal to AV. And so, since this holds true for all vectors V, we would know that B A times B beta times B inverse is equal to A. And so, I will just like draw a line here. And so A beta has to be equal to B inverse AB. And that's how you take a matrix and represent it in a basis. All you need to do is that you need to multiply by B on one side and B inverse on the other side. All right, so for part D, so up until now we've been only doing some basis beta to the standard basis, or the standard basis to some other basis. But now what we have to do is that we have to convert between two bases. So let's say you're given a vector in a basis beta, and you want to convert it to something in a basis alpha. How do you do that? Well, given what we have learned already, one way to do that would be to just go from beta to the standard basis, and then go from that standard basis to alpha. So we just use the standard basis as sort of a midpoint, like going from this to that, and from that to that. And that's it. Right, so for part E, all we have to do is that we have to take a vector, we have to take a vector 1, 1, and we have to represent it in a basis where B is given by our rotation matrix for degree 45. So what do I mean by that? By that, I mean this our matrix B is just cosine 45, sine 45, negative sine 45, and cosine 45 again. And to put that in real numbers, our B is equal to 1 over square root of 2, like that, and that. So that is our B. We have our vector, and all we need to do now is that we need to compute B inverse V. And that B inverse V, as always, will give us V beta. And there are multiple ways of doing it, but the way I like to do it is to look at the fact that if we are computing the inverse of a rotation matrix, that's the same as just taking the rotation matrix, but for negative angles, right? So in fact, if we look at it, B inverse is just going to be cosine of negative 45, negative sine of negative 45, sine of negative 45, and cosine of negative 45, times V, of course. And what this is doing is that it's taking a vector and it's rotating it by negative 45 degrees. So if we have a vector here, 1, 1, let's say this is V. Now BV would have taken this vector and would have rotated it by 45 degrees in the positive axis, in like the positive direction. But B inverse will do the same operation but in negative direction. And so what we'll end up with is just we'll end up with something on the x-axis. Exactly what will we end up with? Well, let's find out. So I'm just going to erase this part. Actually, I will erase the whole thing. And so we want to compute what B inverse V is. Well, V is 1, 1. As we remember, B inverse is just cosine of negative 45, so that's 1 over square root of 2. Negative sine of negative 45, that is also 1 over root 2. Sine of negative 45, that's negative 1 over square root of 2. And cosine of negative 45, that is 1 over square root of 2. And so if we do the computation, that will just end up being 2 over square root of 2 and 0, and which is equal to square root of 2 and 0. And so that is exactly the vector that we'll get mapped to. So it's like, it's going to be on x-axis with the length square root of 2. All right, so part F is sort of a philosophical question. We're given some vectors, v1 to vn, but they're linearly dependent, so they're not a basis. So if you're given a set of vectors that is not a basis, the question is, can you still take any vector and represent it as a linear combination of them? And when you think about it, since they're not basis, they cannot span the whole space either, right? So let's say I take 3 vectors. Let's say I take 1, 1, 0, 1, 0, 0, and 0, 1, 0. We know that these are not linearly dependent, linearly independent. They have to be linearly dependent because we can express 1, 1, 0 as a linear combination of these two. So they're not a basis. So it's not a basis. But then we also know that they cannot span the whole R3. They cannot span whole R3 because all of their third coordinate is 0. So if I wanted them to have a combination that looks like 0, 0, 5, for instance, I can never find alpha betas such that alpha times 1, 1, 0 plus beta times 1, 0, 0 plus gamma times 0, 1, 0 gives me 0, 0, 5, because all of these are just zeros. And one way to see that is that if I were to take these vectors and if I were to make them into a matrix, let's say I were to make the matrix B out of beta 1, beta 2, beta 3, oops. Since these columns are linearly dependent, I would never be able to actually take the matrix B inverse, because linearly dependent columns means a non-full rank matrix, also known as a rank deficient matrix, and so the B inverse never exists. If the B inverse never exists, then that means I cannot always change a basis. There will always be a vector such that I cannot solve like BV equals, so B beta, this system does not always have solutions because B inverse does not exist. And that's it for part F, at least for the algebraic perspective. For the geometric perspective, we can think of it slightly more geometrically. We can say that, let's say we were in the 3D space. And let's see if I can draw this. This will definitely be a challenge for my drawing abilities. So let's say we have a 3D space. This is R3. And we are given 3 vectors that are linearly dependent. To make our life simple, I will make a plane essentially here. So basically, this is one vector, and the other vector looks kind of like this. And the third vector is a linear combination of them. So I'll just draw it like this. So all of these are linearly dependent, and they span a whole plane in R3. So it's like that. This diagram looks slightly weird. So looking at it from some other angle, we can see that there's like this plane in R3. And this plane is spanned by those three vectors. And now the question is, can you express any point in R3 as a linear combination of these three? And the answer is no, right? Their whole span is just this plane. All of their combinations will end up just lying in the same plane because this plane is the subspace that contains them. And so any point that is outside that plane cannot be reached by these points. And therefore, these points cannot construct that point. And so in the example that we saw earlier, if all our basis vectors were 1, 1, 0, 0, 1, 0, and 0, 0, 1, and 1, 0, 0, they would not make a basis because their whole span would just be limited to the the plane where these two things, where the first two coordinates are not zero, so they're like some x and y, and the last coordinate is 0, so it will be the xy plane. Their span is the xy plane, and so anything that does not lie in the xy plane will not be in their span. And so that was it. Thank you.